Okay, hi everybody. Today we're going to be looking at more about confidence intervals. My apologies for the last two videos being quite long. For some reason when I get to start talking I don't seem to be able to stop. Alright, I'll try and put a limit on my amount of talking this time though. I promise I'll try. No guarantees on what actually happens though. I've already wasted about half a minute. Alright, let's get going. Okay, so you remember that last time I talked about why we call it a 95% confidence interval. It's because we take the Z distribution and work out the two boundaries on 95% of our area in between those two boundaries. And if we increase the percentage area that we have in between, then we get a bigger interval. And so that gives us less information about our population mean. If we have a smaller area, then we get more information about our population mean, but we are less sure or less confident about our population mean. So we can't be as categorical. So we're 95% sure that our population mean lies in between these two values. So those two values there, x bar, take 1.96 sigma on root n, x bar plus 1.96 on sigma on root n, those are what you use to calculate your 95% confidence interval, and then we looked at what that meant. So there's sort of this trade-off between the confidence level and also how much we can say about our mean. This is really what this page goes through. I'm not going to fill it in because I don't think it's that relevant. Just to make the point that 95% is the only value which is examinable, so you'll only ever be asked for a 95% confidence interval. But if you think about the distribution of the sample means, so going back up to here, the other way we can actually make this distribution of sample means smaller is by increasing our sample size. So if you imagine this distribution here, then, and that's for a particular sample size, then if we go to a larger sample size, then the distribution of our means is going to actually come in closer to the mean and then peter out there. It's going to come in here and go along there. And so the bigger our sample size, the more amount of area is going to be closer to the mean, and so that's also going to help us reduce our confidence interval as well, or the size of our confidence interval, meaning that we're going to get a smaller confidence interval and we're going to be able to say more about the mean. So that simply comes from the fact that the standard deviation of our distribution of sample means is inversely proportional to the square root of n. So a good question to ask is determining the sample size for 95, or what's a good sample size for a 95% confidence interval. So the bigger the sample size, the more work that the people collecting the samples has to do. So we can't just say, oh, make it as big as we want. So there's also a trade-off here, but we need a big enough sample size to get a relatively good interval that tells us enough about our population mean. So the requirement to be satisfied is to be 95% confident that the sampling error, that is the difference between the sample mean, which we represent by x bar, and the population mean, which we represent by mu, is within an interval of plus or minus e. Okay, so what that means is that we want the difference between our sample mean and our population mean which is just simply x bar take mu So we want our difference between x bar take mu to be between e and negative e, and e is what we call the sampling error. So to represent that in a diagram, say we had something there and something there, and then just make those black so you can see them. So if okay, so what we're saying here, you'll notice that I've just added a little bit. So if this is our interval around x bar, then if we want the sampling error to be between minus e and e, then we want it to be somewhere along this line here. So from there to there is e, and from there to there is minus e. So we want our population to be somewhere here, and we're going to call the width of the whole interval w for some unknown reason. Can't understand why you'd call that w, but there you go. So e, that's the capital E, is the given margin of error. So that's what we call the margin of error. So it's the amount of error we have within our confidence interval, and W is the given width of the interval. So that's our whole width of the interval. We call this the given margin of error because that's how much our population mean strays from our sample mean. So for a 95% confidence interval, if we go back up to where we calculate the formula for calculating the confidence interval, we know that this is 1.96 sigma on root n. The boundaries are 1.96 sigma on root n away from x bar, or our sample mean. So that means that our error is equal to 1.96 sigma on root n. I'll just make that a lowercase n. So what that really means is that the square root of n is equal to 1.96 sigma divided by e. And so that simply means that n is equal to that squared. Because if you square both sides of the equation, you get rid of a square root sign. And so it's just equal to that squared. Okay, now what that's telling us is that to get a certain error, sampling error, so to make our confidence interval so big, then we need a sample size of n. So that means if you say, well, I want my confidence interval to be this big, this formula gives you a way of saying, well, okay, I need to collect this, or I need this sample size, so I need to collect this many values from our original population. We could also find a formula for the width of the interval. So if we consider the width of the interval, which is represented by w, not x, w, then w equals 2e, which implies that e is equal to a half of w. Hopefully that's not challenging anybody too much so far. So if we substitute into the above formula, then which is this one, then we can write a half w there, and then when we when we have a half W here, then to get rid of the half, we can, so it's this over a half times W, so we multiply by 2. So it's just simply 2 times 1.96 sigma over W. And yep, so that's in the denominator, so we invert and multiply. So it's 1.96 sigma divided by a half, so we invert it. When we invert, we get 2, and then we multiply it by 2, so that's how we get 2.196 sigma there. And so that gives us the sample size we need in terms of the width of the interval. You could evaluate 2.196, that's not really that crucial, but the crucial thing is that this is on your formula sheet in the exam. So I know you get your own page of notes, but your Math Studies exam also has a formula sheet associated with it, and this here is given on that formula sheet. So when you're doing the questions, one thing I'd make sure I'd be very clear about is, are they asking for the sampling error? So are they asking for only half, or are they talking about the fact that they only want the sampling error to be a certain size, or are they talking about the width? So you really got to read the question carefully, because it makes double the difference. Okay, so based on that, some questions you might like to try would be, and just before that, this is how you do it on your calculator. So you might just want to go through those steps and have a go on your calculator. If you can't get it, feel free to ask me. So yeah, some questions you might want to try. Questions from 7i.2. There would be questions 1, 3, 4, and 6 from the textbook. And the rest from there are questions 2 and 5 you might want to do in your own time. Okay, alright, so work through these calculator instructions, make sure you're using that to find your confidence intervals, and have some fun if you can.